Okay, we're going to enter in a unit where we use the integral to do different things for us, mainly geometrically, and it's going to be a short unit. We're going to go pretty fast through it. So today we're going to look at finding the area between two curves, which is not that much different from finding the area between the curve and the x-axis. It's just a slightly modified application. So we have to remember that when we found the area between a curve and the x-axis, we started with a rectangle, and then we added up a bunch of rectangles, and then we took the limit of the rectangles as n goes to infinity. So in this unit, we're going to draw lots of representative rectangles. So here we have, find the area between the graph of sine x, which is in red, cosine x, which is in blue, between the lines x equals 0, which is the y-axis, right here, and x equals pi over 4, which just happens to be where the two curves intersect anyway. So the region we're talking about is the region that's enclosed by those boundaries. I want to draw a representative rectangle in this region. So I'm going to put a generic point on both curves and connect them. That'll be the height of my rectangle, and then I'm just going to draw an arbitrary width. And now my question here would be, okay, what is the area of this rectangle? And that's going to be representative of every rectangle in the region. So if we go to coordinate geometry, we could call this point down here x comma sine of x. And up here, same x coordinate, the y coordinate would be the cosine of x. Our width is arbitrary, and so let's label it as dx, like delta x. So the area of this rectangle would be, the height is cosine x minus the sine of x times dx being the width. Now, if we were doing this slowly, methodically, we would create an expression for the area of this entire region with n rectangles using sigma notation. We would then take a limit as n goes to infinity, but then we would just convert this to an integral because that's how we defined an integral in the very beginning, was as a limit of a Riemann sum. So the bottom line is, the area of this entire region is going to be the integral from the left boundary, which in this case is x equals 0, to the right boundary, which is pi over 4, and then I'm just going to use the area expression for my representative rectangle, which in this case is cosine x minus sine x dx. So I now have an integral that finds the area we're looking for, and I would just have to go about evaluating this. So let's go ahead and do that real quick. Antiderivative is going to be sine x plus cosine x, and we're going to plug in our two limits, 0 and pi over 4. I suggest parentheses with a minus sign in between them to keep things straight. So the sine of pi over 4 is the square root of 2 over 2. Cosine of pi over 4 is also the square root of 2 over 2. Sine of 0 is 0. Cosine of 0 is 1. And so our area is the square root of 2 minus 1. Let's look at another example. Here we're asked to find the area in quadrant 1. So that means the x and the y-axis can be boundaries. So in this case, we're going to use this portion of the x-axis as a boundary. And it's bound by the two curves, y equals x squared, which is red, and then the tangent line to the graph of f of x equals x squared at x equals 2. So we're going to have to go ahead and find the equation for this line before we do anything else. So let's go ahead and do that. We're going to use as 2 comma f of 2, which would be 2 comma 4. And then we need a slope at 2, so we need the slope finder, which is going to be 2x. And so f prime of 2 is 4. So the equation of this line is going to be y equals 4 plus 4 times x minus 2, or 4x minus 4. And we can tell from the picture that they intersect at 2 comma 4. We also know that that's because that's the point of tangency. So 2 comma 4 is up here, and we have the boundaries all set. Now, we could draw representative rectangles to set up an integral, or maybe two integrals, to find the area of this region. And I'm going to show you an alternative approach to doing this the way we did in the last slide. So if I draw representative rectangles, I'm going to notice something. Okay, this rectangle goes from the red curve down to the x-axis. But if I drew a rectangle slightly farther to the right, the rectangle goes from the red curve down to the blue curve. So this means there are two different regions to consider here, and those regions change at this point right here. So if I wanted to do this using the method we'd used on the last slide, I'd have to set up two different integrals. One that goes from 0 to 1, and the other that goes from 1 to 2. And that's fine, you can do it that way, it'll work. But I'm going to show you a slightly different approach. If instead of drawing my rectangles vertically, like I did on the last slide, I drew them horizontally, then I'll notice that every rectangle in the region will be uniform. In other words, they'll all go from the blue curve on the right side down to the red curve on the left side. So this means I have another way to approach the area problem, just drawing my rectangles with slightly different orientation. Once again, I want to know what is the area of this representative rectangle. In this case, the y-coordinates are what are the same for these two ordered pairs, these two vertices of my rectangle, and so I have to figure out what the x-coordinates are in terms of y. So this requires a little bit of algebra. Here's the tangent lines equation over here. So if I solve this for y, I'm going to get y plus 4 equals 4x. Divide both sides by 4, and we get 1/4 y plus 1 equals x. So the x-coordinate of this dot here is going to be 1/4 y plus 1, comma y. And then what's the x-coordinate going to be over here? Well, let's see here. That's the curve y equals x squared. And so if we take the square root of both sides, we get positive and negative square root of y equals x, but I'm in quadrant 1. Okay, I'm in quadrant 1, so I know that x is positive in quadrant 1, so x equals the square root of y. And so that's my x-coordinate over there. Now, my width, or whatever you want to call this dimension right here, is not dx, it's dy. And this makes sense because my area expression is going to be written in terms of y's in this case because my rectangles are drawn to different orientation. So, in this case, I want to do right minus left instead of top minus bottom to guarantee that my width in this picture is going to be a positive number. So 1/4 y plus 1 is the right x-coordinate. Subtract the square root of y, and then I'm going to multiply by dy. That's the area of a representative rectangle. And so now the area of the entire region is going to be the integral of that expression. So the integral of 1/4 y plus 1 minus square root of y, but I'm going to write that as y to the 1/2 times dy. Now, what are my limits of integration? I now have to think in terms of y-coordinates. So my y-coordinates begin at 0 down here. And if I was thinking of going upwards, drawing my rectangles horizontally, they're going to stop at a y-coordinate of 4 because these two curves intersect at the point 2, 4, as you see up there. So that's a common mistake that students make is they have the wrong limits. Just remember everything's in terms of y now. So now all I have to do is the antiderivative and plug in these numbers and we'll have our answer. I have 1/8 y squared plus y minus 2/3 y to the 3/2. And we're going 0 to 4. Again, big parentheses with a minus sign. The nice thing here is that everything in the second expression is going to be 0. And we're going to get 16/8, that's 2, plus 4 minus 4 to the 3/2 is going to be 8. So 16/3, 6 minus 16/3 is going to be 18/3 minus 16/3, or 2/3. So that's the area of our region.